Okay, guys, can you hear me? How are we doing? Are there any questions or comments before we get started? Okay, so today's goal is to finish up loose ends about American options. So we have a couple of loose ends. We have a bit left about the infinite or the perpetual American put from last time, and then we have this section 4.5 with the American call on the finite horizon. We have these two loose ends, and we'll see how far we get. If we get through them, then we can start talking about fixed income at the end. So what we were doing is we had this perpetual American put option. And so we had this example where this was from last time. We had the example that Sn would be this usual form, S0 times these coin flips. So we had written this as 2 to the mn, and mn was this symmetric random walk on the integers. Right, so this was our symmetric random walk. So these are IID coin flips. So this is our symmetric random walk on the integers, and this is our stock price. And of course, we also have a bank account. Times 1 plus R. So we see we go up with a factor of 2. We go down with a factor of 1/2. As U and D is equal to 2.5. And R here, I think we choose it to be 25%. Right, so U was equal to 2, D was equal to 1/2, right? So when we put all this together, we're going to get that P tilde and Q tilde are the same, namely 1/2. So we were doing, so last time we were analyzing the picture. We were trying to do heuristics. We came up with, I think we had K was, what did we put for K? Was it 5? No, it was 4. Forget, what did we choose K to be last time? I think we had K to be 4. And so we were doing the analysis last time. Here would be 4. So here we have the stock price. Maybe the stock price. And 4 and 4, we would have that hockey stick. So this picture here, this is 4 minus x positive path. So that's the hockey stick. And so we were looking at saying that, well, when x is small, right, so we have our function v of Sn, right? This was the maximum stopping times tau omega belongs to n plus 1, and so on. and we take E tilde out here of 1 over 1 plus R tau minus N, and then the payoff K minus S tau, positive part, we condition up to time N. So we're interested in figuring out, there were two things we were interested in figuring out. We were interested in figuring out what V is. We were interested in figuring out what is the optimal exercise time. So we were playing with that last time, and so we were saying that, well, when S is very small, so when we're down here, V is just going to be this straight line. So we had our conjecture for V of X. We were conjecturing that the value function should have the form so for small x, so when x is small, then it would be 4 minus x, so we're on a straight line. And then when x is big, it will be different. It will be something like something that we will have out here. It will be a solution to this. Notes all messed up. What would we do when this here was your exercise? And then the other one was here you're going to continue. We were looking at solving V of X being, what was it? It's 1 over 1.25 times 1 over a half. 1 over a half times, and then it was V, and then U was 2, so this is 2x plus V of X divided by 2. We were solving something like this, and we ended up saying that we get 4 divided by x, and then we wanted these two things to be continuous, okay, and we also wanted them to be smooth, so we ended up saying that the critical threshold would be 2 here. Right, so in the picture up here, when I put in this critical threshold, this would be here, right, and then the value function would be this straight line here, and then it will come out. It will come out as this 4 over x when you're bigger. And so in the same breath, we would also have a conjecture for what the optimal exercise time would be. This would be the first time such that the stock price is less than 2. So we spent the last half of the lecture last time trying to come up with this guess, and I think this was about here where we ended. Now we talked a little bit about, okay, so how do we actually check that something like this is correct? And so that's what I want to start today's lecture with. And the questions on up to this point here? Right, so we have a stock price. The stock price is moving, and when it drops down to 2 or below, and then you call it quits and you exercise. Right. So another thing we have done is we know that the probability that tau star is finite, this is equal to 1. So I don't have to worry about this thing being plus infinity, because the set where it will be plus infinity is a null set. So is this optimal, and is this really the price of the perpetual American put option? Well, let's let's try to derive some properties of it. First, we can see up here that if I pick just tau to be n, if I pick tau to be a constant and I pick a constant just to be n, I'll see here that v of Sn is going to be bigger than, it is the maximum. So some properties. So let's do the first one. Set tau just to be n. Well, then we look at the definition, then we get that v of Sn. This is the maximum, right? So this is going to be bigger than just a conditional expectation of 1 over, well, it'll be 1 plus r to the power 0, because it's tau minus n. Tau is constantly equal to n, right? So here, so maybe I should be more specific, right? This is tau of, I said tau of omega to be equal to n for any omega and omega, right? So it's a constant. It doesn't depend upon omega, and then I'll get a 0 here. I'll get k minus, and then it'll be Sn positive part, right? And everything here is measurable. This is equal to 1. I'll end up with k minus Sn positive part. So that's the first property we derive. For my value function over here, it has to be the case that it's bigger than the hockey stick. Okay, so let's have a look. Is this true for the function I have here? And the answer is yes. This function here indeed satisfies this property. Okay, so let's look at some more properties. We're claiming that 1 over 1 plus r to the nth of v of Sn. I'm claiming that this is a super martingale. Okay, so how do we see that? Well, if you look at the formula here, if I were to move, so let's just compare with the European case. Compare with the European case, then you would have that you would be stuck with something like En of 1 over 1 plus r tau minus n, and then you would have k minus s tau. Right. For the European case, here we'll say expiry tau. And so this would be the value. This would be the value of the European put that has expiration date tau. And if this was your v, this was my v of say Sn, then what would that be? Then this would be, I could move this quantity 1 over 1 plus r. I could move it outside. Right, I could write this here as 1 plus r to the nth, and then En of 1 over 1 plus r to the power tau times k minus s tau. And then I could move this to the other side. This is going to be equal to En, I should have tildes everywhere here, 1 over 1 plus r to the power tau, k minus s tau. And what we have here on the right-hand side is a conditional expectation. What we have here on the right-hand side is a conditional expectation of a random variable that doesn't depend upon n. So this quantity here This is a P tilde martingale. Right, so in the European case, V divided by 1 plus R to the nth, this is a martingale. In the American case, there's this maximum or supremum sitting out in front. Here there's no maximum. So in the European case, you're going to get the martingale property. In the American one, what we'll be claiming is that you're not going to get a martingale, you're going to get a super martingale property. So how would one go about proving that? Well, the proof is not very different from what we did here. But there's going to be something about using the formula, and then there's going to be something with the supremum out here. So we have to get rid of the supremum, and instead of getting an equality, we have to get an inequality because we're looking for a super martingale, not a martingale. So let's see how to do that. So to see the super martingale property, we need to show what do we need to show? We need to show that V of Sn divided by 1 plus R to the nth, that's going to have a relationship with, when I look at it 1 point later, V of Sn plus 1 divided by 1 plus R to the n plus 1. If it's a super martingale property, I expect it to go down. Okay, so then I can simplify. I can see that this is the same. I move this quantity here on the other side. I can put it inside the expectation because it's a constant, and it'll eat away most of what I have down here. It'll just leave me with 1 plus R downstairs. We good so far? So this is what I have to show. Right, to see the super martingale property, we need to show this inequality. Yeah, how will I do that? Okay. So to see, let me call this last one for star. We're gonna let say tau hat be an optimizer for the n plus 1 for the n plus 1th problem. So we find out what that means. So if I look at the supremum, so I'm looking at the problem here, not at time n, but at time n plus 1. So take the supremum over tau. Tau of omega f belongs to n plus 1, n plus 2, and so on. I look at the conditional expectation, time n plus 1, 1 over 1 plus R, tau minus n minus 1, and then the payoff k minus s tau, positive part. I'm letting this tau hat be an optimizer for this problem, so that means I can write this here as e tilde n plus 1, 1 over 1 plus R, tau hat minus n minus 1, k minus s tau hat, positive part. So because because tau hat is a stopping time, and it's given that tau hat takes values n+1, n+2, and so on, and tau hat of omega not only does it belong into this set, but it also belongs into the set of n+1, so on. That means that I can plug it in. That means that I can plug it in to this optimization problem. And it has to be a stopping time. It has to take values in n+1, n+2, and so on. So because tau hat is one of those, we have an inequality. We'll have that V of Sn. Like, remember, this is the supremum over all of them. This is going to be bigger than when I plug in tau hat. So this is En tilde 1 over 1 plus R. Then I have tau hat minus N, K minus S, tau hat, positive part. And so let's start to work on what we have on the inside the expectation. Here we need to relate that to something that looks like what we have up here. So we can do that. I need to have something here with an n-1. So let's try to do that first. I have 1 over 1 plus R here. Then I want to use conditional expectation, the iterated part, so I can plug in a conditional expectation at a later point. And then I have 1 over 1 plus R, tau hat minus n minus 1. These will cancel out, so I get back to this one. And then I have K minus S tau hat positive. Okay, so here I used iterated expectations. And I just multiplied and divided by the same quantity. And then I'll use 1 over 1 plus R. And then what I have here, because tau hat is the optimizer, but on the left-hand side, this is my V of Sn plus 1. Because tau hat is the optimizer, I know that this expression here on the right-hand side, this is exactly my V of Sn plus 1. So I'll plug that in. And this is what I needed to prove. So now I have two properties. I have the property that I'm a super martingale, and I have the property that I dominate the hockey stick. So is that true for the function V I have over here? So I dominate the hockey stick. What about the super martingale property? Is that also true here? Is that also true? If I look at this V I have here, is this going to satisfy? Is this going to satisfy that I have a super martingale property when I plug in Sn here and I divide by 1 plus R to the power n? But I'm claiming that this function I have here, this is exactly what this one here is a definition, right? I'm claiming that this concept here on the right-hand side, based upon the heuristics that we did last time, that this is this bracket function we have here. So I'm now deriving properties of this general form over here. O'Shea, he says, no, I don't think this is a super martingale. Okay, so should we have a little check? So let's try to do a sanity check. So we'll make a little note here. So this is like a sanity check. For V of x being 4 minus x x less than 2, and 4 over x bigger than 2, do we indeed have that v of Sn divided by 1 plus r to the n is a super martingale? Well, recall that v of x was equal to this max. It was equal to the max of 4 minus x, and then that European version, which was 1 over 1.25, 1 over 2, v of 2x plus v of x divided by 2. So I'll have that v of Sn, I'll have that v of Sn is equal to the max, right? So it's going to be bigger than or equal to, it's going to be bigger than or equal to if I take x to be Sn. So it's going to be bigger than or equal to if I throw away the first part. This will be 1 over 1.25 times 1 over 2 times v of Sn times 2, so that was my u, plus v of d times Sn. And what I have here, this is exactly equal to the conditional expectation under the tilde measure of 1 over 1 plus r, and it'll be v of Sn plus 1. Which is the super martingale property. So, because you're close, you're saying that something fails with this 4 minus x, and I agree. What is it that fails with this 4 minus x? It's not the super martingale property that fails. What is it that fails at that point? So let's go back. If we had the European one with this random expiry, so if you had the European one, you get the martingale property. You get the martingale property, but now we have the American one, so we have the supreme one in there, and we establish this super martingale property. So it's not the super martingale property that this term here ruins. What kind of a property is ruined by this max of 4 minus x with the other thing? In other words, what led to this inequality here? Could this be an equality? Why did I write greater than or equal to here? No, so U and D are fixed, right? U is equal to 2, D is equal to 1/2. This one here is my U. This is U, this part here, this is my D. The D are not moving. It doesn't just have to be Hoshi. Everybody's welcome to pitch in here. In the European case, I would have the martingale property, and now we're seeing the calculation. We're going to get an inequality here. Where's that inequality coming from? Well, it's coming from this max being here. Right? I write that inequality by throwing away the first part in the max. Right? The maximum of two things will dominate each of the two things. Right? So if I'm throwing away the first term in the max, I'm going to be left with the second term. Right? So the second term is going to be less than the maximum. Like the maximum between A and B is bigger than A, and it's bigger than B. So I'm throwing away the first term, and we're going to get the second term, right? So this is what gives me the inequality. So this is the super martingale property, and this is not a martingale. This is not a martingale because V of x could be strictly bigger than 1 over 1.25, 1/2 V of 2x plus V of x divided by 2. And indeed, that happens in the picture. Indeed, that happens in the picture, right? We're just asking when is this inner part going to be the biggest one? Well, that inner part is going to be the biggest one on this piece here. Like out here, right? So out here we will have that the max of 4 minus x and 1 over 1.25, 1 over 2 V of x times 2 plus V of x divided by 2. You'll have that maximum, this is exactly equal to 1 over 1.25, 1 over 2 V of x times 2 plus V of x divided by 2. In that region here, the maximum is equal to that. And in the other region, in this region here, you're going to have that max over 4 minus x and 1 over 1.25, 1 over 2, V of 2x plus V of x over 2. We have that is exactly equal to 4 minus x. And then at the point, they're going to be the same. And it's also going to be the case that there's like a smooth derivative. Right, so that the presence of this max here that will either be the second term or be the first term, depending on what x is. It is that ruins the martingale property. And instead it gives you a super martingale property. So what you could do instead, so to recover the martingale property, what you do is you stop at the first time Sn hits 2. Because if you stop it the first time that you hit 2, then this part here becomes irrelevant. Then it'll only work up here, right? So what you're doing is you're running your process, and the first time that the process hits 2, you freeze it. Well, that's exactly my toss star. This is toss star. Right, so for arbitrary tors, you're going to have a supermartingale property. Right, so let me say that more precisely. Right, so in general, you're going to have a supermartingale property, and then if you stop it, you're going to have a martingale property. Okay, so we're going to explore this. This is more to come. Oshi, does that make sense to you? And everybody else, does what we're talking about here, does that make sense to you? So the difference is that when you have this supremum for the American options, you will not have a martingale property. You have to be happy enough just having a supermartingale property. So the next thing that comes, okay, so this here was just a sanity check for this guy we have. For this guy we've conjectured last time, we indeed have this property that we proved in general. Okay, so there are more general properties coming up. The third one, this here is what's called the Snell envelope. This is the Snell envelope property. 1 over 1 plus r to the nth v of Sn is the smallest process satisfying 1 and 2. Right, so 1 and 2, let's go back, double check. Go back and double check. So 1 is you dominate. 2, you have a supermartingale property. So this V here appears to be not an arbitrary process satisfying these two, right? You could presumably have, I mean, there are many other processes that will satisfy these two, but there's a smallness property embedded in this definition here, and it's not a surprise because there's a supremum, and a supremum is indeed defined in terms of a smallness property, and we talked about that last time too. We talked about last time that there will be there are many functions that satisfy that function is equal to the max between this quantity and then this 4 minus x. Right? This one here is the smallest such function. Okay, so let's see that. So proof of 3 here, this is the smallest process that satisfies it. So to make headway, let yn be another process satisfying 1 and 2. And then we're going to prove that v, that we're going to prove that this quantity here is going to be smaller than y. Right, so what do we have? So we have from 1 we get that the yn dominates k minus Sn positive part. So this is going to imply that if this is true and this is true for any n, so then if I stop the process, so I'll do y tor min m. So remember what that notation here means. So if I do a min b, this is defined to be the minimum of a and b. So if I stop the process at this time tor min m, m is some number in the natural. Tau is the stopping time. Tau takes values. Tau takes values in n, n+1, and so on. So if I stop it, because this is true for any n, it's going to be the case that this is going to be bigger than tau min m positive part. So this was the first property that we use. So we take y as another process that satisfies 1 and 2. Okay, so y dominates the hockey stick. Okay, everywhere. In particular, if I stop y, it's going to dominate the hockey stick evaluated at that random time. Okay, now we do 2. From 2, we get. Now that's a super martingale property. From 2 we get, and here we also use Dupes optional sampling. If we use Dupes optional sampling, we'll get that the conditional expectation of use the inequality. If I'm looking at 1 over 1 plus r to the power tau min m, and then the payoff k minus s tau min m positive part. I will get that from this inequality here. I'll get that this is going to be less than conditional expectation 1 over 1 plus r tau min m, and then I'll have my y. So this inequality here comes from the inequality up here, and so now it's time to use the super martingale property together with Dupe. Dupe says that when you solve a super martingale, you are again going to get a super martingale, and so here comes that property. Here comes that property. We'll get here that this is 1 over 1 plus r tau min n times y tau min n. And of course, when I'm looking at taus that take values, tau is a stopping time that takes values at or above n. So this thing here is just 1 over 1 plus r to the power n times y n. So I get an inequality. And let's try to figure out what that inequality, how do we get to the end here? So if I take, so I have yn divided by 1 plus r. This here is bigger than what I have on the left-hand side. So I'll write that out here as e n tilde, and then 1 over 1 plus r tau min m k minus s tau min m positive part. And then I can take a limit as m goes to infinity. But there's no m on the left-hand side, there's only an m on the right-hand side. And now I want to move the limit inside. And I can do that because what I have inside here is bounded. So here we're using dominated convergence. Dominated convergence allows me to pull this limit inside. And so m goes off to infinity, tau is finite. I'll get here I'll get m goes off to infinity, tau is finite. I'll get 1 over 1 plus r to the tau times k minus s tau positive part. And so from this I can move the discount factor over here. I can move it inside. So this here implies that yn is bigger than. I'll move this discount factor inside. So 1 plus r tau minus n, k minus s tau, positive part. So from what I had over here, I moved the discount factor to the other side, put them in here, right? And now there's no tau dependence on the left-hand side, so I can take the maximum over tau's, and this is going to give me exactly v of Sn. So this proves that v has this smallness property. You give me another process that has properties 1 and 2, then that other process necessarily must be bigger than or equal to v.
Sorry, I'm just wondering what's the difference between n and m?
It's just because, I mean, m here is something that we're ultimately going to pass off to infinity. So m here, you can take m to be something that is bigger than n. It's because to use Doob, we need some properties to go from, in this case, yn, from yn being super martingale to yn min tau being also a super martingale. Right, so you need the first one is you need tau to be a stopping time. Then the question is, do we can it be any stopping time? So here I did. So I like personally. I always have, this is a pitfall, right? Because the thing I'm worried about is it's not true that. So the warning is about. Right, the warning is if I have a property like if I know so the super martingale property says that you're going to go down on average, but does something like this carry over to saying that y at tau is also going to be less than y0? Right, so what I did was, so by stopping with tau min m instead of tau, we have that tau min m is bounded by m, whereas tau is not bounded. So I'm just making sure that I'm not making a mistake anywhere in here. And the way that I ensure that is that I apply Doob's theorem by finite stopping times. And then, of course, the price that I'm paying is that I have to move m to infinity, right? Because on the right-hand side, I can there's no requirement that tau has to be bounded here. It's just a requirement that tau is the stopping time. And tau of omega takes values between n, n plus 1, and so on. But there's no upper limit here. So this one here has an upper limit, right? This here is a stopping time. This quantity here, right? Tau min m evaluate omega, this takes values in n, n plus 1, up to m. So it gives me this upper bound on the stopping times. And then when I have an upper bound on the stopping times, I know that I will not run into problems of the sort that, yeah, that there are some regularity conditions needed in order to be able to apply Dup's optional sampling theorem. And by ensuring that I'm only applying it to bounded stopping times, I know that I'm not going to be in violation of these assumptions in Dup's theorem. And that's the only reason I'm putting it in. Did that make sense?
Okay.
I just want to make sure I'm
yeah,
not.
That makes sense.
I want to make sure I'm not making a mistake here. So it depends upon, can you get around and use Dup's optional sampling theorem for arbitrary stopping times? And the answer is yes, you can do that. But then you have to be careful about that you're pushing the problem somewhere else. So here I'm wearing both suspenders and a belt, so I know that I'm not making a mistake on these slides here. And I guess the argument we're doing here, this would never in a million years work for the call. I could not do this for the call. Because if I swap the roles of K and S here, so I'll put S over here and K over here, this would not work because that quantity that I would then get would not be bounded by K. It would be bounded by S tau min M. Right? So now I have a problem. Now I have a problem with passing M to infinity because and pulling the limit inside because I don't necessarily have an upper bound that is integrable. And here it's easy because this quantity here is bounded by K, right? When we look at the payoff diagram, there's a bound here. And the bound is in this case 4. But if you swapped it around so you have a call, right, then the call would start going up like this. And there would be no bound. So then this argument here would have to be altered. And indeed, the second part of this class here, we're going to talk about what happens for American call options. Yep. Are there more questions, comments? So this was the Snell envelope property. Still not there. What we have at this point is, so this is where the minimal property comes from. Like that function that we found last time, this guy down here, we could have used, for example, 4 over x everywhere. That would have solved it too, but it's not minimal. Like 4 over x, even when x is smaller than 2, it's still going to dominate the obstacle, but it's not minimal. How do we finish this proof off? So the final step So how do we finish? How do we check? So how do we put the pieces together? How do we put the pieces together and show that tau star really is optimal? Like so. So at this point, At this point, what do we have? We'll have, at this point, we'll have proven that V of Sn, it dominates the obstacle. That was one of the first sanity checks we had. Page 2. That was this property. When I take the function that we had on the first page, it dominates the obstacle. The second sanity check we had was that V of Sn divided by 1 plus R to the nth is a super martingale. Right, so from these, I get an inequality. From these, I would get as before. So from before, we'll get that V of S0 is going to be bigger than this supremum over tau of the conditional expectation. Is that times 0? Is that times 0? So 1 over 1 plus R tau K minus S tau. Yeah, that was the argument we did before. We proved that this supremum, this is the smallest such process. Okay, so here in the example, my V, this is that function we have, this satisfies these two properties. I'm going to be, this one here is the smallest one that has these properties. Okay, so V is just one of them, so I'm going to get this inequality. Like, so to finish it off, we need, so to finish, we need to show equality. And it comes out as, so the way that we do that is, so to do this, we claim, we'll prove that if I take, and we had that on one of the slides, there was this slide here, I think this was a comment that Fauché made, something fails with this 4 minus x. Okay, so to recover the martingale property, we stop it the first time you hit 2, which is this tau star. Okay, so more to come. So there's more to come. This is what's coming now. If we do that, we'll prove that this super martingale property over here can be upgraded. That this is a martingale. So we need to show that we have equality here. And so we will do the upgrade of the super martingale property to prove a martingale property, and the cost we're paying is that we're going to stop it. And why is that sufficient? Well, if that's the case, so if V of Sn min tau star is indeed a martingale, we get, what will we get? Well, first of all, I know that martingales have constant expectation. So I'll get that V of Sn min tau star divided by 1 plus R n min tau star. And this is exactly my V of S0. So now I'll take a limit as n goes to infinity. Right, there's no n on the left-hand side, so, and on the right-hand side, I have something that is bounded. So we're going to use dominated convergence. Again, my function V that I have in the picture, this is a bounded object. This V here, this is bounded by 4. Right, so I can use dominated convergence to pull the limit inside. So here, this is dominated convergence. I can pull it inside. I'll get E tilde. N goes off to infinity. I'm going to get V of S tau divided by 1 plus R tau star. And of course, this is going to be less than the supremum over all stopping times. Like at time, maybe I should make an additional step in here. Like at the at the first time that at that time tau star, this is the first time that S drops below. This is the first time that S drops below 2. It's the first time that S drops below 2. So they, if I were to compare with, K minus S tau star over 1 plus R of tau star, positive part. This is the first time. This is the first time that V becomes equal to the obstacle. So again, this piece here, this is K minus X. The stock price moves, it hits this thing. So at that time, the value function is going to become exactly 4 minus X. The expectation here, right? And this is going to be less than the supremum over all stopping times. Right, because this is just one of them. So then you go back, you now have that V of S0 is less than the supremum, but based upon the supermartingale property from before, we have that it's bigger than, and so now we get equality. So what remains to be proven is this martingale property, and as soon as we have that, we're done with the proof. To check the supermartingale property, we need to use to check or verify the martingale property. We split, and this is inside the expectation. We split inside the expectation. We split omega, so we're looking at E tilde n of Bsn plus 1 min tau star divided by 1 plus R n plus 1 min tau star. So we split inside the expectation, and what we're going to be splitting is the case when tau star is less than n, and is when tau star is bigger than n plus 1. Okay, so what's the first one? Now tau star is less than or equal to n. Okay, so what do we get here? This is E tilde n V. So tau star is less than or equal to n. So the min between tau star and n plus 1, this is just going to be tau star. And times the indicator. And now on the other set, what happens here? So now tau star is bigger than n plus 1. Okay, so then the min between n plus 1 and tau star is going to be n plus 1 because tau star is bigger than n plus 1. So here we get V of Sn plus 1 divided by 1 plus R to the power n plus 1 times the indicator tau star is bigger than n plus 1. Okay, so the first part, we're conditioning on n, tau star n is less than n, all this stuff can go outside. The conditional expectation of this random variable is just going to be the random variable. So that's the first one. Now the second part, this is more tricky. Well, what I can do is, at least I can put out 1 plus r to the nth. I can put that outside. 1 over 1 plus r to the nth. And then I'm left inside here with v of Sn plus 1 divided by 1 plus r. Now I am on the set where I'm bigger than, tau star is bigger than n plus 1. So what do we have here? So what is this quantity here equal to? Well, you know that, so on this set where tau is bigger than n plus 1, Sn has not reached, what was it, 2 yet. So on this set, Sn has not reached the 2 yet because that time comes no earlier than at time n plus 1. Tau star is the first time, right? So it cannot have reached it at time n. So that means that when I'm looking at v, if I'm looking at v of Sn, right, this is going to be equal to, what was it, the max of 4 minus Sn, and then there was this 1/2, 1 over 1.25, and then it was v of Sn times 2 plus v of Sn divided by 2. So now I know that this thing has not reached 2 yet. So what is v of Sn actually equal to? Well, this is going to be equal to, which one of these is biggest? Is it 4 minus Sn, or is it the second term?
Minus Sn.
Where is the stock process? Is it in here or is it out here? Is it in here or is it out here?
I think it's in the first part.
Well, Sn has not reached 2 yet. Tau star is bigger than n plus 1. So where's the stock price at time n? Is the stock price out here or is it in here? It hasn't reached 2 yet. Well, there's no doubt, then it's got to be out here. Right?
Oh, wait, sorry, could you repeat? The tau star,
So tau
I think
star,
I got that concept.
so tau star, this is the first time the stock price dips below 2. So if you know that tau star is bigger than or equal to n plus 1, what can you say about the stock price Sn?
Oh, I see it now. Yeah,
right?
because we're at the time point n+1, but then tau star is yet to come.
Yes,
Wait.
right. So
Okay.
this means that
I got a flip.
that's okay. So this means that Sn is strictly bigger than 2, right? You haven't reached 2 yet. So Sn is floating around somewhere all the way out here to the right. It's not down.
Yeah, I see it now.
Yeah, okay. So that means that the stock price here is actually 1 over 1.2 times, no, 1 over 1.25 times 1 over 2 times V of Sn2 plus V of Sn divided by 2 on that set. Right, so what is this conditional expectation then? Well, this conditional expectation is going to be, now we have a martingale property, this is just going to be, so we have V of S tau star divided by 1 plus R tau star indicator tau star is less than n plus that other term. Now it has the martingale property because it's the second term, so we get that this is 1 over 1 plus R to the nth, and then this will be V of Sn times the indicator tau star bigger than n plus 1. Just a sanity check. Everything here, it really is Fn measurable. Right? That's because I know this set here by the definition of a stopping time. This is an Fn, and this here is the complement, so that's also going to be an Fn. So this here was a little detour. Now we can just combine them. We can write this here as this is equal to V of Sn min tau star divided by 1 plus R n min tau star. And that's what we set out to prove. So this was a long loose end. We finally got tied up. This is what it will take to proceed. If one wanted to do, this is what's called verification, and this a lot of calculations anyway. We started out last time by building up some intuition, namely for this function v. Today we pushed it a bit further. We started looking at properties. Of this abstract concept here on the right-hand side. We derived a bunch of them. So one of them was it dominates the obstacle, it dominates the hockey stick. The other one was a super martingale property. And then there was also a minimal property. So those were listed here as 1 and 2, and then the last one was this Snell envelope property. That where's page 5? 1, 2, 3, 4. Where's page 5? So there's page 5. The minimal property was, it says that if I take another stochastic process that has these properties of being above the obstacle and being a super martingale, I can combine them and prove that any other such process must necessarily be bigger than this object. And how did that come in the specific example? Well, the way that came in that specific example had to do with how we created this v. Right? We could have used a function v that would just have been 4 over x everywhere, right? So it would have dipped up if one would just have looked at v of x being 4 over x. That would also have been satisfied properties 1 and 2, and then it would have dipped up here. Like that would have been this guy here. But that's not minimal. Right? It also dominates the obstacle, but you can find one that's smaller And so this idea of smallness, this comes from the third property. Okay, so given all that, could we then complete the verification step? Could we piece it all together and show that indeed the optimal time to exercise a perpetual American option is given as the first time that the stock price dips below 2. This should be a 2 here. Right, this is the same. This is the same as the first time that V of Sn becomes K minus Sn positive part, right? And so, yeah, but the way to do that is we use the two properties we already have, and then we find just a random time such that you have a martingale property here.
Sorry, I got confused again. So the first time that Sn dips below 2,
Yep.
that's tau star.
Yes.
And then like here you have 4 minus Sn. So I got confused again. So why is the like the result we got the 1 over 1.25 times 1/2? I think I'm still confused. Like I understood it for a second, and then after thinking about it, I got confused again.
Maybe we should try a fresh piece of paper. Right, so we have our function v of x. This was this 4 minus x, and what was it, 4 over x? This is when x is small. This is when x was less than 2, and this is when x is bigger than 2. And then I have my tau star. This is the first time that Sn dips below 2. But that would be if I look at this function here, right, this quantity here, 4 over x, this is going to be strictly bigger than 4 minus x, if and only if x is strictly bigger than 2.
Oh, I see. I think I just plugged in tau star as 2 in my head.
No. So tau
Yeah,
star
okay.
no. This here is then the same as the first time that V of Sn is equal to 4 minus Sn.
Well, okay, I see. Thank you.
Other questions, comments? So there are, in general, maybe just some additional remarks, and then let's take a little break. So in general, there are many optimal stopping times. So don't expect uniqueness. So that's not true. So the value function is. So value functions are of course unique. But it's not true that for optimal stopping problems that the stopping times are unique. Another way to describe these optimal stopping times is so we had this Snell envelope. So what you do is you write Sn V of Sn divided by this 1 plus R to the n. This was a super martingale, right? So you will write this, and it's the smallest of such a thing. So what you do is you write this as a martingale. So this here is a martingale. And if I want to get a super martingale, what else should I do? If I have a martingale, if I have a super martingale, I want to write it in terms of a martingale. How do I do that? Well, I need to correct the martingale terms with something. What should I do? Should I add or subtract something here? So if I have a martingale, I have a super martingale. Super martingales have a tendency to, do they have a tendency to increase or decrease? I should add something. Do you want to add with a plus or with a minus? Subtract. I like it. We subtract here. And this one here is then this AN. AN is going to be increasing. So if we want to get the minimal property, we should then look at tau, say star. This is the first time I want this thing stopped to be a martingale. Okay, so I really don't want this increasing property to start coming into play. So tau star is just the first time that AN becomes positive. So you stop as soon as AN moves. This here is called the dupe decomposition. So that's, if you want to pursue this Snell envelope, the Snell envelope property says that this thing here has to be minimal. Okay, so an optimal stopping time is going to be when you look at its decomposition. You want it really just to be a martingale. So as soon as this thing starts moving, you kill it, you freeze it. And so in general, this is an example of an optimal stopping time. Are there any other questions or comments? Otherwise, I suggest that we take a little pause here and then reconvene in 10 minutes or so. And again, as usual, we have to use a different Zoom link. Any other questions before we call it quits? Okay, then I'll see you in 10 minutes.